In this series of videos, I'd like to walk you through the inner workings of my custom renderer built specifically for Astortion. It consists of 4 vastly different passes, but I want to start with the most important one, the parallax pass. Its task is to render each parallax layer in the native resolution, upscale it, and then composite it with the rest, providing a smooth parallax scrolling while keeping each layer pixel perfect. We'll talk about the composition process in the next video. Today, we'll use a simple scene with only one layer to explore a technique called deferred shading. We start by rendering all opaque objects into a so-called G-buffer. In this case, it consists of 2 textures. The first texture stores information about the base color. This process is relatively straightforward. We sample the texture assigned to a given sprite and store the resulting value. Notice that even though we're rendering only opaque objects, we can still use sprites with an alpha mask. We simply discard any transparent pixels and leave only the solid ones. If the sprite uses a lookup texture or a palette, we also resolve it during this step. The second texture is used to store information about the normals. This will be useful later when rendering lights. Normally, a normal would be a 3-dimensional vector telling us which way a surface at a given point is facing. But since we're working in 2D and our meshes are flat, all normals would simply face towards the camera. So instead, we're gonna modify the normal for each vertex to face outwards, as if our mesh was just a slice of some 3-dimensional object. This way, for any given fragment covered by the mesh, we'll know roughly in which direction the surface is. Before we save our normals into the G-buffer, we'll need to pack them. Both the x and y components of these normal vectors range from -1 to 1. We'll first add 1 to them, and then divide by 2, so that they fit into the red and green channels respectively. Sometimes, however, we may want to have a more granular control over the normals of our sprite. In that case, we can provide them as an additional texture that will be rendered directly into the G-buffer. With the buffer prepared, we can move on to the next step, rendering lights. The basic idea is to take the base color from the G-buffer, multiply it by the light, and save the result into the output buffer. This is where the name deferred shading comes from. Instead of calculating lights for each object in the scene, we defer the computation and perform it only once, at the end. Now, because light blends additively, we need to add all the lights illuminating a given fragment to get the final value. But instead of adding the lights first, we can use the distributive property, multiply each by the base color, and then add them together. Let's see this process in practice using a point light. We start by generating a mesh that covers the entire area affected by the light. In this case, it's a circumscribed square. We'll render this mesh into the output buffer and use the fragment shader to do our calculations. First, we need to find the light intensity at a given fragment. There are a few factors contributing to it. First, we have the base intensity. It's a per light variable that dictates how bright the light can be. Next, there's the natural fall-off of the light. The farther away from the source, the dimmer it gets. We may also want to limit our light to a specific angle, in which case it will fade towards the edges. Since the origin of our square is also the center of the light, we can use the fragment's coordinates in local space to compute its distance and angle. We can then use these to derive the radial and angular fall-off respectively. Another factor affecting the intensity is the direction of the underlying surface. We only want to illuminate surfaces that face the light source. This is where the normals in our G-buffer come into play. We can find the direction of the light by taking its position in world space, subtracting the fragment's position, and normalizing the result. Taking the dot product by the normal vector will tell us how much the surface faces the light. You can think of it as projecting the direction vector onto the normal. When the two are perfectly aligned, the result is 1. As the light becomes perpendicular, the result goes to 0. And when the light crosses to the opposite side, the value becomes negative. To get our intensity factor, we just need to clamp this dot product. To do these calculations, we only need the x and y components of our normal vectors. This leaves the blue channel of our normal texture available for other uses. So let's make it control the influence of normals on the final intensity. The value of 0 will disable normals, while 1 will leave it as is. We can now multiply all 4 factors together to get the final intensity of our light. Then we can multiply it by the light tint to get the final light color, multiply that by the base color, and add the result to our output buffer. If we repeat the entire process for each light in our scene, we end up with a final shaded image. Let's introduce one more variable called volumetric intensity. It will allow us to control the volume of the light. We'll multiply it by the light color and add the result to the shaded color. Notice how increasing the volume makes the light visible, even if there's nothing behind it to illuminate. You can think of it as adding a layer of fog or dust in front of a layer. Other types of light are rendered in a similar way, but their intensity factors may vary. For instance, a global light covers the entire screen and has the same intensity everywhere. Both normals and fall-offs don't affect it. The final thing that's missing is shadows. I purposefully left them out because they influence the light differently than other factors. Before a light is rendered, each shadow caster in its proximity is rendered into the output buffer. It doesn't modify any of the color channels though. Instead, it uses the stencil buffer to create a sort of mask. The light is then rendered only inside the mask, leaving the shadowed area untouched. A shadow caster is a special mesh that, coupled with a vertex shader, can produce a projected shadow. We can create these meshes offline for any sprite that needs shadows, or at runtime when using procedural geometry. We start with a basic mesh outlining the object. Then we double all vertices making up the contour, like so, and set their normals to be perpendicular to the closest original edge. In the vertex shader, we can take the dot product of the light direction vector by the vertex's normal to see which vertices face away from the light. Again, for such vertices, the dot product will be negative. Offsetting them in the opposite direction will produce a projected shadow. With the shadow casters ready, we can use the stencil buffer to composite the shadow mask. In case you don't know, this buffer contains an additional 8-bit value for each pixel that we can modify and test. For instance, while rendering our shadow meshes, let's set the stencil value to 1. Now when rendering the light, let's test if the value is equal to 0. If the stencil test for a given fragment fails, it gets discarded and doesn't affect the result. This works, but now the insides of our sprites are always shadowed, meaning that normals are ignored. To fix this, let's use the original sprites to reset the stencil value before rendering the light. So we start with the shadows, cut out the sprites, and then render the light. It's better, but there's still a problem whenever a shadow is cast at another shadow caster. Ideally, we only want to cut out the shadow cast by the sprite itself, while keeping any external shadows. Fortunately, we don't need to write a specific value to the stencil buffer, we can also increment it. Let's start from the beginning. Just like before, we first render the shadow meshes, only this time we increment the stencil value, so each fragment will end up with a value equal to the number of shadow meshes that cover it. Next we render the original sprites, this time decrementing the value. This way, parts of the sprite covered by only one shadow will be reset, but the fragments covered by 2 or more shadows will stay above 0. If we now render the light where the stencil buffer equals 0, the result works as expected. So far so good, but as you may remember, this technique only covers opaque objects. Rendering semi-transparent things using a deferred renderer tends to be difficult, mainly because blending normal vectors doesn't make sense in this context. We can still render semi-transparent pixels, however, they'll have to inherit the normals of the underlying geometry. Sometimes it makes sense, for instance when rendering decals, but we'll talk about better transparency support in the next video, when we introduce multiple parallax layers, and talk about effects such as depth of field, anti-aliasing, and light shafts. For now, this pretty much wraps up the process of rendering an individual layer. Some of the ideas presented here were adapted from Unity's 2D renderer, so if you're interested, I left some links to its source code in the description. Anyway, thanks so much to all my patrons, thank you for watching, and until next time.